I'd like to thank the organizers and thank everybody for sticking around before lunch to listen to my talk. I'm going to talk today about this multilinear local TB for square functions. This is a joint work with Ana Grau de la Heran and Lucas Oliveira. Quick overview of what I want to do is just a short motivation, and then talk about some global versus local testing conditions for square functions, and then I'll present the multilinear TB or local TB theorem. And I really want to emphasize here what the difficulties were in extending this to a multilinear setting, and just very briefly kind of the proof strategy. There isn't really enough time to do a lot. But, okay. For motivation, I just want to start looking at kind of classical Littlewood-Paley theory. If we take a function psi that looks like this, or its Fourier transform looks like this, and form the convolution operators here, these can be thought of as some sort of frequency projection operators. And Littlewood-Paley theory tells us that this actually generates, for appropriate psi, an equivalent norm on LP for p between 1 and infinity, but I'm just going to worry about this inequality here. And I want to look a little closer at this. What type of conditions do I need on psi? What type of conditions were important here for this inequality? Because certainly the function that I've chosen there, that's not necessary. Right? So the important properties it has plenty of decay, right, being a Schwartz function, smoothness, and cancellation is the other thing. And by cancellation here, you can see the Fourier transform at 0 is 0, which means this thing has integral 0. So we're going to work to generalize these operators both to a multilinear setting and a non-convolution setting. So that's what the next slide is going to do here. And throughout this work, or throughout the presentation, I'm going to assume some basic decay and smoothness and really concentrate on what a weaker cancellation condition is. So these are the kernels that I want to replace my convolution kernel. And you can think of this as if you were to take a convolution kernel in, say, Rn and restrict the x's to all be x1, 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 all of the same thing, that would generate an operator like this. Right? So these are, in some sense, a restriction operator. There's one way to make them. Right? But we're going to look at this general class of them instead. And our operators that we look at are just integration against these kernels. And then the square function, or what we call the square function, is exactly this. So on the last slide, this thing was psi t convolved with f. Right? Now we're looking at a multilinear setting. Okay. So, like I said, what cancellation conditions do I want on the kernel in order to guarantee that this square function, this s sub theta t, is bounded on LP spaces, or product LP spaces? So for a little bit of a review, kind of a lead up, these are some results that are known. Right? In the linear case, this sort of mean zero condition, right? This is the kernel has integral 0 in the y variable. These operators are bounded just like the psi t that I showed before. And the same kind of thing happens in the multilinear setting. Right? If we take something that has integral 0 in that second variable, or in the y1 through ym variables, again, we get LP bounds. But these conditions are too strong. Right? This mean zero condition is too much. We can weaken this quite a bit. And that's the direction we're going to go. And the first way we can weaken it is by requiring some sort of Carlson measure condition. So I want to quickly define what a Carlson measure is here. If you're not familiar with Carlson measures, you're going to be able to get through just knowing kind of what the shape of this thing is and know that we're testing on that. We're going to test some function on that. So it's a measure on Rn plus 1 plus, which is Rn cross 0 to infinity. And it's such that when you take a cube, cross the length of that cube, it's controlled by just the measure of the cube. So we're going to use this as a size condition for our theta t of 1. Right? So long story short, this Carlson measure condition just says that theta t of 1 is not too big in some sense. Right? Instead of requiring it to be 0, we just require that this is a Carlson measure. So this holds in the linear case. And if you notice, this just holds on L2 now. Due to kind of technical reasons going through the Fourier transform, we lose things in LP. And this extends also to the multilinear setting. Right? So this is kind of the way we start weakening these conditions. And in fact, this is both of these are necessary and sufficient. Right? So that means this is a Carlson measure if and only if this thing is bounded for some indices like that. Right? And again, we're restricted to dealing with L equal 2 here. But I said we wanted to weaken these cancellation conditions. Now I told you that these are equivalent. That means I need to weaken some other way, right? And the way we're going to weaken these is instead of testing on a globally defined function 1, we're going to test on locally defined functions. Okay? So in some situations, it's not very nice to have to look at the entire function 1. So that's, we're going to go to the next thing. So we're going to think of defining some sort of collection of functions that are local approximations to 1. And these are a collection of or pseudo-accretive systems. Right? So the way you can think about this is these BQs are approximations to 1 on some cube Q, right, on a dyadic cube Q. This is just some size condition so we can deal with it, so we can control it in some sense. And then this is saying that it's accretive. It's somehow an approximation of 1. Right? It doesn't vanish. And here's some examples. And you can see, I mean, if you just have a function that's positive and nice, everything's going to work out fine here. The interesting ones are you can take a function like this, as long as when you integrate, kind of the total average, the total mass average is positive, even though when you look on a subcube, that may have cancellation. Right? So these types of functions are completely fine. They're allowable. And they can also blow up. Right? So all of these were defined by, well, they're listed on the next slide, I think, when I state the theorem. These are defined in some of these other works on the linear version of this. And they're saying exactly, assuming those size and regularity conditions, that you can replace that Carlson condition with this Carlson-like local testing condition. Right? And that's sufficient for square function bounds. Okay? So other theorems like this have been proved in the singular integral setting. The precise theorem I have stated here is in a work by Hoffman. But I cite some of the other ones, the work leading up to it. Right? So this is what we extend to a multilinear setting. And we have to ask a little bit more from our functions. So like I said in the last one, or before, this is kind of like a restriction operator. So in order to make this restriction, we have to somehow pass from individual averages of the B's to a product average of the B's. So that's where we have to require this compatibility condition, which I'll give here. Okay. So this says that somehow, instead of looking at the product of the averages, I have to be able to compare it to the average of the product because of it, the restrictive nature, or the restriction nature of this. And I think I'm going to have to get moving here. But so this is, again, we have a Carlson-like testing condition leading to square function bounds. Okay. Just a note on the compatibility condition here. If you take just nice functions here, it works. If these are just positive and bounded, of course it works. So this compatibility condition isn't too restrictive. We have things that are there. But also, we can't just take any systems of accretive functions. For example, this one that was that had cancellation, or that had mean 0 on this subinterval, this does not satisfy our compatibility condition. Okay? So somehow, when these systems vanish or degenerate at the same scale in the same place, our proof breaks down. So whether it's necessary, I don't know. But somehow when these things degenerate in the same place, they violate this compatibility condition. And I have no time to go through that in any more detail. Okay. So a quick sketch of the proof. we're just going to go through this equivalence with the Carlson measure. So we're going to look at this thing and show that that thing is a Carlson measure. And we look at it by looking at the function that we're trying to average, right? So that thing's a Carlson measure if this GQ is, on the average, is uniformly bounded, right? I should say. When you average this function over Q, that's uniformly bounded in Q. Right? And this is just some picture of what that thing might look like, right? And what we're going to do is break it into these sets, right? This old measure theory trick that we look at where the function is bounded by n, and then just bound the average, and then use the size of this set, right? Say that this set is small where that function is large. So now the goal here is to find a sufficient n to say that this is bounded independent of Q. Right? And we're going to pass through this paraccretive system somehow. Okay. So that's the goal is to balance those two terms in some way. And the way we do it is we break into large and small scales and argue in two different ways. And the idea is, on large scales, these are a good approximation to 1, so we can use the previous theory that we had, the sort of theta t of 1, 0 type conditions. And then on the small scales, we do kind of a clever decomposition to essentially shove it down to lower scales. Right? So this is going to involve some sort of recursive argument saying that it works on large scales, and if it doesn't work on that smaller scale, well, then view it as a large scale and shove it down to even smaller scales. And based on the conditions, that works. Okay. So we start by looking at this box, Q times the length of Q. So this is one that you would test that function on. And we do kind of the same idea decomposition as the Calderon-Zygmunt decomposition or the Whitney decomposition that we saw before. You take a Q and say, do we like it or not? And the first one we don't like based on, I should say, this is the selection criterion. So when that thing is, when this is larger than a half, we don't like the cube, so we throw it out, and we just keep breaking down until we find one, the first one, that's smaller than that, and then we have a nice decomposition here. And passing back through this, what we get is, if you look along the bottom here, wherever a red cube is sitting, the function is bad. That's where the function blows up. Wherever there was not a red cube, the function is nice. Right? That's where things are working well. And through these accretive assumptions, we can get a control on essentially where the function is bad. Okay? And this fraction of the set essentially tells us that part of the set is never too big. So this being less than 1 here says we can always control a certain fraction of that set. And that allows us to shove down to lower layers. So again, I'm going to go very quick through this. Just a quick idea how you handle the large scale is we can introduce these averages. So this is how we bring the actual b's into the equation because they're good on the scales that we talked about, or on the scales that we decomposed there. And then we can shove them in here. And now through some paraproduct argument and multilinear square function bounds, we can get this thing bounded. Now the smaller scales is a little more complicated, and I'm out of time. So I'm going to go even faster. The idea is we go through and say that we can make this, based on how small this set is, and that this thing is well behaved on certain sets E, we can hide this term behind that one. Right? If we take n sufficiently large, it's going to make that one smaller, and then we can control the size of that set in this way. Okay. I can't go into any further detail, I don't think. But that allows us to control this, and we essentially push that forward to this relationship, look at the soup over all Q's, we get some uniform bound plus that same parameter that we're pushing through smaller scales to that same bound, right, where this alpha is smaller than 1. Then you just solve this equation, and the thing is bounded, and it's a Carlson measure. Right? So I skipped many, many details. You have to worry about all sorts of technical details, whether that's finite to start with or different things like that. But a 15-minute talk, we don't do that. So, and then there are a few other results that, again, I think I'll skip over. So thanks for listening.